Let's go through a particular problem here. I have a 12 kilogram mass sliding at 6 meters per second along a frictionless floor towards an ideal spring. The spring has a spring constant of 45 newtons per meter. Now, if you've watched the other video or you understand this stuff really well, then you should be able to, I could have given you other information and you could have calculated that. So the mass is going to hit the spring and they will stick. So the first question is, how far does the spring compress? Well, we're dealing with energy here. The ideal, we have the only forces acting on this mass at any point here when it touches the spring. We have this spring force right here. We have normal force this way, weight this way. These aren't doing any work at all. This is the only thing that is doing any work, and it is conservative force, so therefore energy is conserved. E initial equals E final. So this is K initial plus U initial equals K final plus U final. Formula for kinetic energy is, presumably you said 1/2 mv squared with great enthusiasm. The formula for potential energy is, I'm assuming you said which one, the one associated with this ideal spring, which is 1/2 kx squared. And again, this x right here deals with how far it's been moved off of equilibrium. So as this thing compresses, that will be x, is equal to 1/2 mv final squared plus 1/2 kx final. That's initial squared. So initially, this has not been compressed at all, so that is 0. At the final, when it's completely compressed, that is equal to 0, because if it's not 0, that means it's still moving. So I'm left with 1/2 mv initial squared equals 1/2 kx final squared. In other words, all the kinetic energy at the beginning is equal to all the potential energy at the end. 1/2s cancel out, and I'm left with x final is equal to m over k, we'll put in the intermediate step, vi squared, and so x final is equal to the square root of m over k times v initial. And just working through the math there, we end up with the compression will be the square root of 12 over 45 times 6 equals 3.098 meters. So that's how far this thing is going to compress. So if the mass then sticks to the spring, we now have a mass basically attached to a spring on a frictionless floor. It's undergoing simple harmonic motion because the only force acting on it is the force from an ideal spring. I have an amplitude now. I need to figure out, I know that my generic formula for position for something in simple harmonic motion is an amplitude times the cosine of omega t plus phi. Well, if I start this thing, if I got time is equal to 0, let t equal 0 at maximum compression, and I make that direction positive and make maximum compression positive, that means I'm starting at my peak, my maximum value, which is just cosine, and so phi is equal to 0. My amplitude, well, we just calculated that. That's 3.098 meters times the cosine of omega t. I need to figure out omega. Well, from the previous video, we've already calculated a formula for that. Omega is equal to the square root of k over m, which is equal to the square root of 45 over 12. And so 45, 12 divided by square root 1.9365, and that would be radians per second. And so this becomes 1.9365 radians per second times time. That is the formula to describe the position. My velocity is going to be those multiplied together. So 3.098 And lo and behold, we get 6 meters per second. It'll be negative 6 meters per second sine of 1.9365 radians per second times time. Because don't forget, my velocity is a omega, negative a omega sine omega t plus phi. I'll throw it in there. My acceleration is going to be negative a omega squared cosine of that. So my acceleration is going to be, well, I multiply those together. So 1.9365 times. And I get a negative 11.619 meters per second squared cosine of 1.9365 radians per second times time. Now, so I now have 3 equations to describe the motion of this mass here that is attached to the spring as it oscillates back and forth, where that is positive out that way and it is negative in that direction. How long does it take for it to actually go there and come back? Well, we have a couple ways of doing it. Let's think through it with the math here, and then we'll do something slightly more generic. So this equation right here, I know that when time is 0, I'm at my amplitude, but I'm trying to figure out when do I get back to where I started. So that happens when 1.9365 times time is equal to 2 pi. So time, this is the time when it gets back to where it started, is going to be, this is 3.245 seconds. That's how much time it takes for the object to go there and back. We can do it slightly more generically and actually derive a formula for it. So I know that when omega t is equal to 2 pi, and so the period, the time it takes for something to happen, a repetitive motion to happen once, is going to be 2 pi over omega. And so that is a formula there. If I use that value for omega there, so this becomes 2 pi square root of m over k. So we have a formula now for period. Now, a couple other questions we can ask on this. What's the period of the spring? Well, we just calculated that right there. We could have gone straight into the formula or thought through it. How long will it take the mass to stop the first time once it hits the spring? Well, that's from the time, so if again, it first hits the spring at this point at equilibrium, it then reaches maximum compression, and then it will start oscillating back and forth. I know 3.245 seconds is how much time it takes to go all the way there and back. Therefore, the time it takes to go half that distance is going to be half that time. And the time it takes to go a quarter of that distance will be a quarter of that time. Quarter of going from either middle to extreme or extreme to middle. So the time it takes to stop when it first hits is going to be a quarter of that. So time to first stop becomes 0.811 seconds. And the magnitude of the acceleration at that point, well, I can just recognize that this right here happens to start when time is 0 at the maximum compression. And so my acceleration at that point is, well, right there.